各位好，欢迎参与本次的 On Virtual Hardware 网络研讨会。在今天的会议中，我会解释如何使用 On Virtual Hardware 来运行和测试连接到云端的 IoT 装置。这是本次的网络研讨会的流程和内容。我们将从介绍 On Virtual Hardware 开始，了解它如何融入 CI 工作流程，然后再介绍 Virtual Sockets Interface， 也就是 vSocket， 它如何在 On Virtual Hardware 上提供安全的链接。在 Demo 部分，我将介绍 AWS MQTT 范例应用程式。您将了解如何从 Keil Studio Cloud IDE 进行建构和运行程式。最后，我会介绍如何使用 GitHub Action 在 CI 工作流程中测试这样子的云连接。什么是 On Virtual Hardware？ 您可以将 On Virtual Hardware 视为等效于虚拟机器，但用于嵌入式物联网设备。虚拟硬体目标是基于 On 的处理器，并提供功能精确模型，可模拟软体的行为，但将底层的硬体的复杂性做了抽象化。它可以在云端基础设施中运行，确保快速和扩展的执行，但它也可以在本地端运行，消除开发人员必须取得硬体或电路板才能进行开发的依赖。在之前关于 On Virtual Hardware 的网络研讨会中，我们使用简单的入门范例来展示 On Virtual Hardware 如何用于 CI 工作流程。在这张图中显示了 Project 托管在 Repository 中的流程。您可以启动 CI Pipeline， 对程式进行建构以及测试，然后将结果返回到储存库中。如果发现了问题，开发人员可以在本地端进行调试并尝试修复错误，然后更新程式到储存库中，并再次启动 CI 工作流程。除此之外，真正的产品总是会与外部进行交互作用，因此 On Virtual Hardware Target 可支持用于模拟此类的外部设备的虚拟接口。物联网设备通常使用不同的连线方式，例如透过 Wi-Fi 或 Bluetooth 将数据资料发送到网络和 On Virtual Hardware 目标。这种连接方式通过 Virtual Socket Interface 或简称 vSocket 来启用。因此，对于云端连接，你的 Application Stack 通常会使用一些 IP Socket API 函数，然后依赖 Ethernet 或是 Wi-Fi 的硬体驱动程式来执行通信。对于 On Virtual Hardware Target， 此 Socket API 是需要与 vSocket 接口连接，而 vSocket 接口又会使用主机的 VSD Socket。这与您的 Windows 机器或是 Linux 伺服器与 Internet 的通信也是一样。有关 vSocket 接口的更多详细内容，可以在 On Virtual Hardware 的文件中找到。从您的装置与 AWS、Azure 等云端服务进行通信，您可以使用该云端服务特定的 Connector Client。为了实现跨不同平台扩展的灵活和应用， On 维护了几个开源的软体组件，其中安全的部分支持 Embed 加密。IoT Socket 组件定义了抽象 IP 通信通用的 Socket 接口。有了它，您可以在不同的 TCP/IP Stack 上使用相同的 Socket API， 例如 MDK Middleware 提供的 Network Stack 或 Lightweight IP。您还可以使用不同的通信接口，例如 Ethernet 或是 Wi-Fi， 并且使用 On Virtual Hardware 目标所支持的 IoT Socket， 也就是 vSocket 接口。因此，通过这个概念，您可以实现您的物联网应用程序，使其在不同的网络 Stack 且不同的硬体接口上以相同方式运行，并且还可以在 On Virtual Hardware 目标上运行，以及在云端中执行您的持续整合测试。为了证明这个概念可顺利运行，接下来我们将介绍一个参考范例。我将使用 AWS MQTT Demo 范例， 顾名思义，它将展示如何将设备连接到 AWS 云端服务。该项目支持真正的硬体开发版。在这个情况下，它依赖 Ethernet 或 Wi-Fi 接口来建立与 AWS IoT 核心服务的安全连接，然后使用此 IoT MQTT 协议将自己的数据发布到 AWS 的 MQTT Broker， 并订阅该 Broker 的 Target。我们可以使用 AWS 站点的 MQTT Test Client 来验证通信是否顺利。该范例还运行在 ARM Virtual Hardware 目标上。在这个案例中，它使用主机操作系统的网络上所实现的 vSocket 接口与外部世界通信，但它的运行方式完全与连接到 AWS IoT Core 并运行通信 MQTT Broker 的方式相同。
So let's go and check the application example. It is provided as a GitHub repository, and in the README file, you can find a brief description to get started and useful references. The application is implemented using CMSIS concept that allow us to easily integrate third-party software components into it. The project configurations are defined using CPRJ files, that is CMSIS project description format, that can be used with different IDEs for project development and compiled with different build environments. There are two targets currently supported in this project. One is an IMX RT1050. This is a Cortex-M7 based device from NXP, and for connectivity it will use a Wi-Fi module from Espressif. And another project configuration is made for a virtual hardware target, also with a Cortex-M7 processor that will use a vSocket interface for communication. The structure of this application is quite universal, so the project can already be ported to different platforms, but we also plan to support new targets with it, both as a real hardware boards with different connectivity options and also virtual CPUs. So stay tuned and check this repository to see how it evolves. This repository is ready to use. We can clone it on a local machine, import project CPRJ files into Keil MDK, build the project and run the program on a real hardware board if we have it, or on the virtual hardware target that is part of Keil MDK. And this flow was already demonstrated by my colleague in a previous webinar session and well explained in the Get Started example and virtual hardware documentation. So we will not demonstrate it here, and instead we will try a different flow using Keil Studio Cloud. And for that, we need a copy of this repository that we can work with. So we can just create a fork, and I have already one well configured for me, so I'll just switch to it.
我们先简单介绍一下 Keil Studio Cloud。它是由 ARM 所提供基于浏览器作为开发环境的 IDE tool， 可用于物联网机器学习和更便利的开发工具。由于它是基于浏览器，因此不需要额外的安装流程，您只需要使用 ARM 账户登录就可以开始展开开发工作。它的编译器可以提供具有 C、C++ 语法支持、ARM Compiler Build 服务、Git Source Code 控制和其他可使用的 plugins。它可以通过浏览器与在桌面上的开发板进行沟通，您可以进行 debug 和串行连接，这有助于快速评估基于 CMSIS、RTX、FreeRTOS 或 Embed 的软体设计。您可以在一系列的硬体开发板上运行您的程式，并自行调试软体。不久的将来，也可以在我们的虚拟硬件上运行。现在，让我们看看 Keil Studio Cloud 如何在我们的范例中发挥作用。
Now let's see how Keil Studio Cloud works in action with our example. We go to our browser, then go to keil.arm.com, and here we have a link to Keil Studio. Just click on it. You may be asked for your credentials to an ARM account. I have already used one before, so it gets picked up and I'm getting logged in automatically. It may take a while, so please be patient with it, but after some time you will see familiar IDE environment in your browser window. Here it is. If you have an active project in your environment, it will be already open. In this case, it's a fresh setup, so there is no active project yet, but you can see the hardware board that I have on my desk and which is connected to my laptop through the USB is recognized, and well, is already a good thing to have. So let's go ahead and import an existing project. We just need to provide a URL to our GitHub repository. I copy it and paste here, name, and press import. Keil Studio Cloud clones the repository to its environment and imports the project configuration from the CPRJ file. Currently, it supports only real hardware targets, so it gets configured based on this CPRJ file, and the support for projects with virtual hardware targets will be added to Keil Studio Cloud soon as well. So the project is already good to be built with a special build project button, but it won't work on the device because it lacks some configuration parameters. If you check the example description, so here you will find all the details on the device commissioning and how these parameters need to be set up. We do this manually in this case because it's a reference example and we can change it directly in the code. In your production devices, of course, you could use some automated way to provision these parameters. Returning to the example, let's find these files with the parameters. They are AWS_client credential.h and AWS_client credential_keys.h. In my hardware example, I'm using a Wi-Fi, so I need to provide the Wi-Fi credentials for it. It's very straightforward. It is just Wi-Fi SSID and Wi-Fi password that I have generated for this demo. Other parameters need to be obtained from AWS because they are required to actually establish a secure cloud connectivity. So let's proceed to AWS console. For that, here we are, and just search for IoT Core and proceed to corresponding service. Here we can manage the devices that can connect to AWS IoT. We can see them here under Things. And there is already one thing that I have defined that corresponds to my device, and I'm going to use for my connection. You can always create more things if you don't have any, or if you need more, you can create them as a single or as a set of them. And the details of this are explained in the documentation, so I will not go too much into the details. It is important to save locally the certificates that belong to these things, that they get used later for your embedded code. We can also use this area to monitor the MQTT traffic from our device. There is a test client connected to the same broker as our device. Then we just choose all topics to be observed here and display payload as strings and subscribe. So now all the topics received by the broker will be seen here as well. Back in the Keil Studio, we can also access the AWS resources through the AWS Toolkit. This is an extension that I have already enabled on my side. Then there is a corresponding icon, becomes available here. And in this area, after providing my AWS access keys, I can connect and explore available resources. In the IoT area, we can see the same thing as we have just seen in the console with the certificate, the policy. We can also create new things if we need to, or we can just use available information. For example, we can copy an endpoint that we need to provide as an address for our MQTT broker. We can copy the name of the thing and put it here. For the key credentials, we need to use the files with the certificate and the private key that were provided when the keys were generated. I have already prepared that on my side, so we'll just copy it right here in the certificate, and this is the key. There is a special formatting required, so please check the documentation for details how it should be entered. Now we have all parameters provisioned to the device and can switch back to our project and trigger program build. It will take some time because the project is quite extensive with lots of files, but it still will be much faster than on your local PC. So in less than a minute, we should get our build done. You can see the progress bar running really fast, yeah. And almost there. And here it is. So the build is finished. We're getting the binary file locally on the PC, and then we can just run the program on the hardware. Prepares the debug communication, then it loads the firmware. Now we can see again a progress bar for loading the image. And after that, it starts the program. Here it is. So the program is running. First, the SDK is initialized. Now we're connecting to Wi-Fi, establishing the TLS connection, and sending MQTT messages. Our device also subscribes to the same topics and receives them back from MQTT broker. Now, if we change to our MQTT test client in AWS, we can see that it also receives these hello world messages that our device is sending to the broker. So the communication flow is working correctly. With ARM virtual hardware support being added to Keil Studio Cloud in the near future, this application can be run in the same manner on the virtual processor without any hardware boards. But as mentioned before, ARM virtual hardware also provides a great solution to run your continuous integration workflow.
我们使用 GitHub Action 在每次程式更改时触发 CI， 这将启动一个 GitHub Runner。我们先前准备的环境是一个托管在 GitHub 上的虚拟机器，使用 AVH Client， 也就是一个 Python module。它允许我们部署 AWS 中的 ARM Virtual Hardware Instance， 并在那里运行我们的 CI 工作流程。为此，所需的全部参数都安全地储存为 GitHub Secret。特殊的 YAML file 定义了需要在 ARM Virtual Hardware 上执行的操作流程。在这个项目中，具体来说，我们也使用 GitHub Secret 来储存 IoT 设备的调试参数，然后分析串行接口的输出，以验证执行结果。我们预期部分的 work message 会从成功的 MQTT 通讯而来。
Now let's go back to our project repository and see how all this is implemented. GitHub workflows are stored in a specific directory here and defined with the YAML files. We have just one workflow implemented, and here we define when it needs to be triggered. So on every push, pull request, and can be done also manually. There are environmental parameters defined here that are required to access an AWS service and deploy an instance with ARM virtual hardware there. You can see they get obtained from GitHub secrets, and I'll show you later how to set them up. The value for these parameters you need to obtain from AWS, and we provide a simple CloudFormation template that prepares all the resources for you and gives you an output with the necessary parameters. Or you can always set them up manually if you're well familiar with AWS environment. Then we implement actual jobs to be run on the GitHub runner. We check out our repository code. Then we set up the Python, and we install an AVH client that we will then use to run our AVH instance. As you have seen in the Keil Studio Cloud, for this project to work, we need to commission our device with some connectivity parameters. This is the MQTT broker endpoint, the name of the thing on the AWS side, and the client authentication certificates. All that is also stored in GitHub secrets here. So you don't need to keep this information exposed in your code in the repository, but the values gets provisioned into the header files right before the build on the virtual machine, and then they disappear when the instance is terminated. Then we use AVH client to deploy an instance with ARM virtual hardware in AWS backend and execute specific steps there as defined in AVH YAML file that we will look at later. Once this is completed, we retrieve from the AWS the images that were built, the output from the console, and store it as the result of the workflow run. Now let's check where the secrets are defined that we are using as our environmental variables to run the workflow. We can change to settings, and then under the secrets, in the actions area, you can see the list of secrets defined for this repository. Note that by the fork, when you make a fork of the repository, the secrets don't get transitioned, so you need to define them in your fork from scratch. So I have the secrets already defined here. These ones specify the AWS access and parameters required to run an instance with ARM virtual hardware. This is you would need for any application, and specific for this project we also need some device commissioning parameters to specify the broker name and the authentication configuration. So you can see that once you define those parameters, you cannot see the value anymore. We can just click on update and change the value if we need to. So by the IoT thing name, it's quite straightforward. I can just set my thing again and update it. Now let's check the AVH YAML file in the code. It is located right here, and as you remember, it is used by the AVH client and specifies what needs to be executed on the AWS EC2 instance on top of the ARM virtual hardware. So in this file, we can specify additional parameters for the AWS. Here we give the version of ARM virtual hardware AMI, as well as an EC2 instance type to start. Then there is an area with the files to be uploaded to S3 storage bucket in AWS. And here we do upload the source code and project files to get the build of the program, and some scripts and configurations to run the test. Then there are steps to be executed, the actual commands to run on EC2 instance, and to build and run our program, we are going to use a build.py file, and for that install some additional dependencies for it, and then run this file on the Cortex-M7 target. Once it's executed, we retrieve the files from it. This is the built images and console output. Now let's see how this workflow runs. We go to the actions. Here we can see a list of workflows. In our case, it's just one. And I have run it already a few times. It takes from 6 to 8 minutes. And we can just look inside of one of these runs. Here it is. We can go right in it. And here we can see a list of all the steps that are part of this run. We set up the job, we check out the repository on the GitHub runner, set up Python, set up AVH client, prepare our environment additionally, and then most interesting part is running the tests, which is actually execution of the AVH client with AWS backend. And we start a new EC2 instance here. Yes, you can see it right there with an ID provided. Then we upload our workspace, install there all the necessary modules, and then build the program. There are many files to compile, so it then completes successfully, and then we run this image on a virtual hardware target, and you can see this is the output of the console, same as we have seen in the serial UART from the real board on the Keil Studio cloud side. So the execution runs and then it completes successfully. Then we terminate the EC2 instance and tear down all the resources that we used. Then we just archive the output that we have received and complete the job. If you look back in the summary of this run, we can see that there is a results artifact stored, and if we save it locally, we can see what's inside. There is a console output. This is basically this serial output log that looks the same as on the real hardware UART, and there is some built output with an image file, map file, and that we can use to reproduce the issue. And this concludes my demo.
在今天的网络研讨会中，我们了解了 Virtual Socket Jekyll， 它可以允许在 ARM Virtual Hardware 目标之上运行可连接云端的应用程式，这和在真实的开发板上运行的方式相当的类似。此外，还看到了带有 AWS Extension 的 Keil Studio Cloud， 我们将参数传递到我们的设备，接着 Build Project， 最后在真实的开发板上运行。随后还展示了一个基于 GitHub Action 的 CI Workflow， 它依赖 AVH Client Command Line Interface 来驱动一个在 AWS 中的应用程序，并在 ARM Virtual Hardware 目标上运行此类的连接云端的应用程式。